Welcome to Section 5-4, Stats students. Good to see you. We're finishing off Chapter 5, our distributions, probability distributions. So in Section 5-3, we did binomial distributions, right? Two possible outcomes. We've still got success and failure, but not everything has two possible outcomes. So if there's one of the different types of distributions is called multinomial. Binomial has two possible outcomes. Multinomial has many, right? Multi. So this is a probability experiment. Each trial has a specific but not always the same number of outcomes. So maybe, for example, if you do an online survey, I'm going to simplify it because some of them that I've talked to or done have a lot of different options, but maybe your online survey is agree, disagree, or no opinion. Right? Three possible outcomes. Again, remember, success only depends on what the researcher is looking for. So maybe the researcher is wondering how many people agree. That would be success. Whatever it might be. Or, sometimes your stats teacher says to you on a scale of 1 to 4, how do you feel about binomial distributions? 1 is I don't have a clue, and 4 is I totally know what's going on. So you have 4 different possible outcomes, and maybe to me, success is a 4, because I want to see the people who feel 100% confident about this. So that would be a multinomial distribution or multinomial situation. So in Section 5.3, we talked about requirements for a binomial distribution. Here's 4 requirements for a multinomial. So you've got to have a fixed number of trials. I'm asking a specific number of questions. Maybe it's 1, maybe it's 10, but I've got a fixed number of trials. Each trial has a specific number of outcomes. So agree, disagree, no opinion, three possible outcomes there. The trials are independent, so one trial doesn't affect the other. It's one of those, if you answered agree, go to question 5. Well, that would be dependent, right? If you answered disagree, you wouldn't go to question 5. So that would make it dependent. And last but not least, the probability of a particular outcome remains the same. So maybe it's 1 out of 3 is your probability of that outcome. We don't change it up mid-course. So those are our 4 requirements. So let's look at this formula. This formula does look a little bit overwhelming, and there's a lot of words. I took this out of the book, so if you are looking for more explanation, I don't know if you realize, but you do have a stats book, and you could look things up in there. But if we're looking for the probability of X, here's the thing. X is going to be more than one thing happening. If you do a quick read through the practice that's right below here, there's more than one thing happening. So the formula looks a little bit huge, but it's not as bad as it looks once you know what you're talking about or where to put things. So the probability of some events X occurring, could be more than one thing, is n factorial, so your number of trials, right, or your sample size, over your first event factorial times your second event times factorial times your third event factorial. You keep going until you finish all your events. And then you multiply that by the probability of event 1 success to event 1 times your probability of event 2 success to the event 2 times the probability of event, and you keep going from there. It looks a little messy. Underneath that formula, it does say that all of your X sub numbers added up equals your number of trials, and all of your P sub 1s added up equals 1, because remember, P is the probability of success, and probability always adds up to 1. This formula, the first part of it, does remind me of the probability of like the word Mississippi that we did back in chapter 4, where we do like 10 factorial over the number of m's factorial times the number of i's factorial. I don't know if you remember that, but that's kind of reminding me of the first part of that formula. And then the second part does bring me back to earlier in this chapter. So let's do a practice. A box contains 4 white marbles, 3 red marbles, and 3 blue marbles. How many marbles do we have in that box? 10 marbles, right? This first sentence right here does nothing more than tell us probabilities. If I stopped there and asked, what's the probability of drawing a white marble? You would say, oh, well, that's 4 out of 10 because there's 4 white marbles and 10 to choose from. So that first sentence tells us probabilities. That's going to be our P's. A marble is selected at random. Its color is written down. It's replaced each time. Find the probability that if 5 marbles are selected, 2 are white, 2 are red, and 1 is blue. All right, so this right here, 2 are white, 2 are red, and 1 is blue, is my probability event. That's what I'm looking for. I just write X because there's a lot going on, but 2 are white is going to be my event 1, 2 are red is going to be my event 2, and 1 is blue is going to be my event 3. So I want all 3 of those things to happen. When I pick marbles out, write down the color and replace them each time. Notice my favorable, my possible are not changing because I am replacing them. Here's the big question, N. What is the number of trials? Some people might think it's 10 because that's how many marbles I have in my box, right? However, how many marbles am I going to select? I'm selecting 5 marbles, so that is my sample size. Again, the 10 tells us the probability of different marbles happening. So I'm going to set myself up a fraction here to do the first part of this. So n factorial. So I'm picking 5 marbles, so it's 5 factorial. My denominator is just how many marbles of each kind do I want to pick. So I want to pick 2 whites, 2 reds, and 1 blue. So that first half of my problem is done. Now I need to go to my probability of success to the x power. So I'm going to multiply this. Sometimes the trickiest part about this is getting your calculator going. So if this is white, the first thing is white, what's the probability of drawing a white marble out of that box? So the probability of success is 2 out of 10, right? Because that's how many marbles, white marbles I have out of how many marbles there are. Oh, wait, sorry, I did that wrong. I was looking at the wrong spot. Probability is up here. So white, there's 4 white marbles. I'm drawing 2, so my probability is going to be 4 out of 10. So 4 out of 10, if you want to write it as 2/5. 2, the number of white that we want to draw, second power. So this number right here will always be your exponent. So my next exponent will be 2, and my last exponent will be 1. So here's my x2. So what's my probability of drawing a red? I'm going back up to this. There are 3 reds. So my probability of drawing a red is 3 out of 10. So 3 out of 10 to the second event. This is my red, so second power. And then blue. So probability of drawing a blue is also 3 out of 10. And that's going to be, I want to draw 1 blue out of there. So that's going to be to the first power. So here is my white probability to the power of how many whites I want. Here's my red probability to how many reds I want to draw. And here's my blue probability to how many blues I want to draw. So that has got to go into our calculator. That's the trickiest part sometimes. So if you're going to type this in your calculator, you don't have a fraction bar, I would put parentheses around that, 5 factorial, or do 5 factorial, which I believe is 120, divided by your product of the 2 factorial, 2 factorial, 1 factorial. Multiply by these fractions, turn them into decimals if you want. It'd be 0.4, 0.3, and 0.3 if you can see that far. Take a break right here. Do the math on your calculator. Make sure. I ended up with a 0.130 when I did my rounding. I think it was a 0.1296 or something like that. So then I'm going to round that up to 130. So my probability of drawing 2 reds, 2 whites, and 1 blue is about a 13% probability. So unlikely to happen, right? Not a really great probability, but we did the check. So that's multinomial. We've got many things happening here. We're asking the probability of more than one thing happening. So let's set up this second problem. So we know that the probability that people choose to go to a movie, to dinner and a play, or to shopping are these things respectively. Everybody knows respectively means in order, right? So here's our three options. We could go to a movie, we could go to dinner and a play, or we could go shopping. This was pre-COVID. We can't do these things right now. So we've got our probabilities. Notice, again, the first sentence gave us the probabilities. So here are our P's, probability of success. Find the probability that out of 5 randomly selected people, 3 choose to go to a movie, 1 chooses to go to dinner and a play, and 1 chooses to go shopping. So what is my N? How many people am I selecting? My number of trials is 5 again, right? Because that's how many people I'm selecting. It doesn't matter how many people we use to figure out those probabilities. It's the number of people we're choosing. So my probability of X, here is my statement that's asking 3 go to a movie, 1 goes to dinner and a play, and 1 goes shopping. So numerator is my n factorial. We said that's 5 because we're choosing 5 people. Denominator, 3 are going to a movie, so 3 factorial. That's my x sub 1. 1 chooses to go to dinner and a play, so that's my x sub 2. And 1 chooses to go to shopping, so that's my x sub 3. So 3 factorial, 1 factorial, 1 factorial. And then I'm going to multiply that by my probability to the x sub whatever power. So probability of going to a movie is 0.5, 50% probability to the 3rd power. Probability of going to dinner and a play, this is dinner and a play, is 0.3, 30% probability of that, and 1 person is going there. And then probability of going shopping is, what here, shopping 20%, 0.2, and we're wanting 1 person to go there. Setup is done. Now comes the fun part, the calculator. Do a quick pause. Make sure you calculate this out the same as me. I ended up with a 0.15, 15% probability that if we pick 5 people, 3 are going to a movie, 1's going to dinner and a play, and 1 is going to go shopping. I'd be the one shopping. So that's a multinomial probability. I want to talk about a Poisson distribution because this one's really an interesting one and people get stuck on this. Don't get stuck on this. It's going to be okay. But a Poisson distribution is when your n is super large and your p is pretty small. Your probability of success is pretty small, but you're picking a large sample or a large number of trials. Independent variable usually occurs over a long period of time. It's usually a rate. So it's used when your density of items is distributed over a given area or volume. I'm going to put rate on here. So for example, couple examples that came around. If we're looking at farming or something like that, the number of plants per acre. We've got ourselves a pretty large sample size. Errors in a manuscript, right? Manuscript is very large. We can pick things out over that. So here's my requirements for a Poisson experiment. X is the number of occurrences over an interval. It's a rate. The occurrences occur randomly, like think about typing up a paper or something, the number of errors, it's just random. It just happens. The occurrences are independent of one another. So one error does not affect another unless your hands are on the wrong spot on the keyboard. And The average number of occurrences over an interval is known. That average number of occurrences is actually called lambda. We've got ourselves a new Greek letter, everybody. So that's always exciting. Might want to go back to that formula and symbol sheet. So our formula for calculating using the Poisson distribution. So right here, I don't know if you can see it, right there, it looks like that. That equals lambda. And that is a rate or an average or mean number of occurrences. Rate or mean. A lot of times you can figure out lambda is equal to n times p. If you've got that information, that might be helpful. Here's my formula. The probability of x with lambda, so x semicolon lambda, is equal to e to the negative lambda power times lambda to the x power all over x factorial. X is a counting number, a whole number, and E is a button on your calculator. If you've done pre-calc maybe you did, or advanced algebra and trig, you might remember doing natural logs, LNs. E is the inverse of an LN. It is a button on your calculator. Look for it. I do have under here E is approximately 2.718, but we're going to use the E button just like for pi. You use the pi button, not 3.14. All right. So I'm going to help you with lambda. The formula is actually looks weird, but it's not as bad as it looks. So let's do a quick example here. In a Poisson distribution, I've got a 400-page manuscript, and there are 200 randomly distributed misprints. So if a page is selected, find the probability that it has exactly one misprint. So here's what it's asking me, right? Exactly one. That's my x. My lambda, I need to know this. Notice there's no n's in here. Lambda is going to be equal to, and I'll probably tell you what you need to find, the average number of errors per page. So if I'm going to figure out lambda, and I'm going to do the average number of errors per page, so everybody knows per means divide, right? So errors, there's what, 200 errors over 400 pages. So I've got about 0.5, a half an error per page. That's my lambda. So now when I go to do this, and it's, I don't want to scooch up so you can't see, probability of x lambda, well, it's asking me exactly one misprint. So 1 with a 0.5 because that's what we just calculated. So this one, again, it comes down to calculator once you got it set up. E to the negative lambda power, so e to the negative 0.5 power times lambda to the x power all over x factorial, so 1 factorial. Double check, find that E button. If you can't find it, please let me know. A lot of new buttons that we're using on these calculators. When I did my calculations, I ended up with the probability of 1 with a 0.5 for lambda is about 0.303. Should put a approximately. So a 30% probability that you are going to find one misprint on a page if you just flip that book open and look at it. All right, let's do one more. I think it's the last example. So, returned mailings. A mail order company finds that 1.5% of their mailings are returned because of incorrect or incomplete addresses. In a mailing of 200 pieces, find the probability that none are returned. find the probability that 3 are returned. So 2 questions. So here's my first one, right? I know that none is going to be my x, but I don't know my lambda, x lambda. So lambda is going to be the same for both of these problems. Lambda is the number of returned mail, the average number of returned mail. So lambda equals average or mean returned mail. Well, in this case, I could figure this out because this was that thing where n times p might be helpful, because I've got a mailing of 200 pieces, and this is the probability that the mail is going to be returned, right? That's just kind of there, they put it out there. So I'm going to end up doing 200 times that 0.015, and my lambda is going to end up being, I think, 3. When I do that math, double check me. So in both of these questions, lambda is going to be 3. In the first one, it says find the probability that none are returned. So now that I've got the hard part done, x is 0, lambda is 3, I can set up my formula. So it's e to the negative lambda power, so negative 3, times times lambda to the x power, all over x factorial. Remember, 0 factorial is 1. We're not dividing by 0 here. You'll get the pattern down. You start with your negative lambda, use the same lambda, and then do your x. All right, so when I did the math for that one, 0 returned mail, the probability of 0 with a lambda of 3 is approximately, it's pretty small, 0.050, I think. Was it a 0.0498 or something like that? So about a 5% probability that none of the pieces of mail will be returned. So, I mean, that's pretty low probability, right? Not likely. So find the probability that 3 are returned. So I'm going to change my x, make it a 3. And my lambda doesn't change. My lambda is still a 3. So x and lambda. This one I wish I'd picked something other than 3 because that is confusing. There's lots of 3's and I want to make sure you know where they're coming from. So this is going to be e to the negative lambda power times lambda to the x power all over x factorial. Basically, in this problem, if you put a 3 somewhere, you're going to get it right because there's a lot of 3's. When I did this one, the probability of 3 pieces of mail being returned when I've got a rate of about 3 returned mail is going to be equal to about a 0.224. So 22% probability that 3 pieces of mail will be returned, which makes more sense because they are finding that 1.5% of stuff is returned because they've got bad addresses. All right, don't get too stressed about lambda problems, about the Poisson distribution. I'm going to help you as we go with those, but the multinomial, please make sure you've got those. I'm going to really give you hints on the lambda. If you've got the lambda down, the rest of the problem is not hard, as long as you know your E button and just setting up the formulas and getting those guys, getting them into your calculator, set up, all that. So that is it for section 5.4 and the end of the chapter. Thanks for sticking it with it, and thanks for doing such a great job. I will see you next chapter.